Like a tidy little solar system. A central nucleus, electrons neatly orbiting around it.
The classic picture.
Very intuitive. Right. But what if I told you that inside this, well, seemingly simple structure, there are two wildly different quantum universes at play, operating at energy scales so vast they almost seem disconnected. And yet they do communicate.
They absolutely do. It's fascinating.
So our mission in this deep dive is to unravel precisely that mystery. How do these two profoundly different realms within the atom whisper to each other? How do they bridge this almost unimaginable energy gap? Today, we're embarking on a deep dive into the atom revisited, a unified analysis of electron orbitals and the quark-gluon substructure of the nucleus. Our goal, really, is to bridge that incredible energy and scale gap within the atom, revealing how its tiny, violent core subtly influences the electron cloud, the part that dictates all of chemistry and interaction.
And when we talk about an immense chasm of energy, we are absolutely serious. I mean, just consider this. The typical energies for electron interactions, the stuff of chemistry, they're measured in electron-volts, EV.
Okay.
But the nucleus, the forces binding it together are so strong, the energies were in millions of electron volts. MeV.
Millions. Wow.
It's 1,000,000 times greater.
Yeah.
This huge separation typically lets us treat them independently, almost like they're in different universes.
Yeah.
Yet, as we'll see, there really is a connection. A subtle one, but definitely there.
It's a mind-boggling difference, isn't it? So, okay, let's maybe leave behind that simple miniature solar system model most of us learned. The modern quantum mechanical understanding of the atom is, well, it's far more nuanced and honestly far more exciting.
Indeed. While, Bohr's model was revolutionary for its time, introducing quantized energy levels, it hit its limits pretty quickly. He dramatically expanded our view, moved us beyond those defined orbits to a three-dimensional, probabilistic description. Yeah. An electron state is described by this thing called a wave function, CI. And here's the really fundamental point, maybe a bit counterintuitive. The square of that wave function, CI22, it doesn't tell you where the electron is exactly. No. It tells you the probability density of finding it in a given spot. So an electron isn't really tracing a neat path. It's more like a probability cloud.
A cloud. Okay.
And what's absolutely pivotal for our discussion today is this concept called nuclear penetration. It's the, frankly, astonishing fact that some electrons, specifically C electrons, have a non-zero probability of being found inside the nucleus itself.
Inside? How is that even possible?
Quantum mechanics. It was completely impossible in the Bohr model, but it turns out this is the main gateway, the primary way these two otherwise separate realms communicate.
That's a huge shift in perspective. So if we can't pinpoint an electron's location, how do we describe these probability clouds? How do we know where they're likely to be?
Well, we have a very precise language for that. Quantum numbers.
Yeah. Right, the quantum numbers. And understanding these is going to show us the communication channels, you're saying.
Exactly. They define the state of the electron.
Okay, so first up is the principal quantum number, Lang-$. That defines the main energy level and kind of the average distance from the nucleus, the size of the shell, basically.
That's right. Higher means higher energy, generally farther out.
Then there's the angular momentum quantum number, $. This tells us the shape of the orbital, right? Like $1 is an s orbital, which is spherical.
Correct. Well, $1 gives you a p orbital, dumbbell-shaped. Then you get more complex d and f shapes as $. Increases.
And the magnetic quantum number, $, that specifies the orientation in space. Like for p orbitals, you get 3 of them along the x, y, and z axes.
Precisely. TPX, pi, p, z, u, all. It tells you how that shape is oriented.
And finally, spin quantum number, $. That's just an intrinsic electron property, spin up or spin down.
Yep, it's intrinsic angular momentum. And those orbital shapes, especially the difference between U's and the others, are absolutely central here. As you said, sorbitals are uniquely spherical. But even more important for us, they are the only orbitals with a non-zero probability density right at the nucleus, $2.
Only the s orbitals.
Only the s orbitals. Now, the p, d, and f orbitals, they have these different shapes, dumbbells, clover leaves, more complex things. Crucially, they all have what we call nodal planes, or surfaces.
Nodal planes, meaning zero probability.
Exactly.
Yeah.
Regions where the probability of finding the electron is 0. And for p, d, and f orbitals, one of those nodes goes right through the nucleus. So their probability density at the nucleus, it's basically 0.
I see.
So this simple geometric fact means that any interaction that relies on the electron literally being at the nucleus, well, almost exclusively going to involve those electrons.
It's like the s electron is the only one close enough to actually feel the nucleus directly in that way.
That's a great way to think about it. It's the only one that gets right in there.
That's such a critical point. And just to round out the electron side, we have rules for how these electrons fill up the orbitals, right? Aufbau, Pauli, Hund's rule.
They dictate the electron configuration, making sure each electron has its unique set of quantum numbers, setting the stage for these very specific interactions.
Okay, we've spent some good time in the electron cloud. But to really get this whisper, we need to dive into the core, the nucleus. For a long time, yeah, just protons and neutrons. But you're saying it's way more dynamic, a seething sea.
That's a good description.
Yeah.
Precisely. The standard model of particle physics tells us protons and neutrons aren't fundamental. They're baryons, composite particles.
Made of quarks.
Made of quarks. A proton is 2 up quarks and 1 down quarks, gives it its positive charge. A neutron is 1 up, 2 down Z, electrically neutral.
Okay.
And holding them together with this incredible force is the glue of the strong force. Particles called gluons.
So if it's just 3 quarks glued together, is it that simple inside?
Huh? Not even close. This is where quantum chromodynamics, QCD, comes in. And it has some really peculiar, almost weird properties. Quarks and gluons have this property called color charge. Just labels, really red, green, blue. Any particle we can actually observe, like a proton, has to be color neutral, effectively white.
Color neutral. Okay.
Now here's a really fascinating bit. Unlike photons in electromagnetism, gluons themselves carry color charge.
Wait, the force carriers carry the charge?
Exactly, which means gluons can interact directly with other gluons. This self-interaction is a huge reason the strong force is so different, so powerful at certain scales.
That is wild. Gluons interacting with each other. And if they're bound so strongly, does that mean we can never pull a single quark out?
That's right. It leads to 2 key phenomena. First, asymptotic freedom. At really short distances, deep inside the proton or neutron, quarks behave almost like free particles. They barely interact.
Yeah.
But then there's color confinement. This is the mind-blowing part. If you try to pull quarks apart, the strong force doesn't get weaker like gravity or electromagnetism. It actually gets stronger.
Stronger? How?
It's incredibly powerful. So strong that you can't isolate a quark. If you put enough energy in to try and separate them, that energy actually creates new quark-antiquark pairs right out of the vacuum. These instantly bind up to form new color-neutral particles.
So you can't pull one out because you just make more particles instead.
Precisely. It's like stretching a rubber band, but instead of breaking, it just spawns more rubber bands. No isolated quarks.
Wow.
So a proton isn't just 3 neat valence quarks. It's this dynamic, constantly churning sea. You've got the valence quarks, sure, but also a swirling cloud of virtual gluons mediating the force, and these fleeting sea quarks, quark-antiquark pairs that pop in and out of existence constantly.
A seething sea is right.
It is, and it's the collective emergent properties of this whole dynamic system that the electrons ultimately interact with, however subtly.
Okay, given all that complexity, it really makes you wonder why we usually can treat the electrons and nucleus separately in, say, chemistry. And the answer, you mentioned, lies in something called the Born-Oppenheimer approximation.
Absolutely. This approximation is, well, it's foundational for much of chemistry and physics. It works because of the huge difference in mass.
Right, the proton is way heavier.
About 1836 times heavier than an electron. And heavier nuclei even more so. What this means is that electrons are zipping around incredibly fast compared to the nuclei, which are relatively sluggish, almost stationary from the electron's perspective.
So the electron sees a fixed nucleus.
Pretty much, yeah. It sees the nuclei as clamped in place. And conversely, the slow-moving nucleus just feels a kind of time-averaged blur of the fast electron cloud around it.
That difference in timescales lets you decouple their motions.
Exactly. For most calculations, you can solve the electronic motion for fixed nuclei and then figure out the nuclear motion later. It works remarkably well.
And the consequence is that clear energy hierarchy we see. Big electronic energy gaps, smaller vibrational ones, even smaller rotational ones.
And way down at the bottom, these tiny, tiny nuclear spin energies.
Right.
And here's the beautiful part, really. The subtle connection we're hunting for today, this electron-nucleus communication, it lies precisely in those tiny, neglected coupling terms that Born-Oppenheimer usually lets us ignore.
So we do ignore them usually, but they contain the key.
We treat them as small perturbations, and they are incredibly small. Let's put some numbers on it again. Electronic transitions, maybe 1 to 1,000 electron volts. typical chemistry.
Okay.
These hyperfine splittings we're talking about, they're down around 10 to the last to 1066 eV, micro-electron-volts, sometimes even nano-eV.
Whoa. That's millions or billions of times smaller.
Exactly. Compared to nuclear excitations up in the millions of eV range.
Yeah.
It's a staggering difference, but it's within these minuscule hyperfine splittings that the nucleus encodes its secrets for the electrons to read.
Here's where it gets really interesting. So despite that huge energy difference, these tiny effects are real. They're measurable.
Oh, absolutely measurable with modern techniques.
And these minute shifts and splittings in the electron's energy levels, that's how the nucleus whispers to us.
That's precisely it. Let's look at some specific ways this happens. First, there's the isotope shift, sometimes called the volume effect.
Isotope shift. Because different isotopes have different nuclei.
Exactly. Different number of neutrons means a slightly different nuclear size, different charge radius.
Right.
Langle, R2 wrangle. The nucleus isn't a perfect point charge.
Right.
This slight deviation from a point charge inside the nucleus, it subtly changes the potential energy for electrons that go in there. And which electrons go in there?
Ah, the S electrons. Because they have that non-zero probability at the center.
You got it. Only the S electrons really feel this volume effect. So by measuring these tiny energy shifts for different isotopes, physicists can figure out how the nuclear radius changes as you add neutrons. It's a direct probe of a collective nuclear property at size.
Very cool. What else?
Then we have the big one, usually. Magnetic dipole hyperfine coupling. This is often the dominant effect.
Okay, magnetic. So it involves magnetism.
Yes. It comes from two things interacting. First, the nucleus itself can have a magnetic dipole moment, Vecchi mu. This happens if the nucleus has a total nuclear spin, Vecchi mu, greater than 0. Think of it like the nucleus itself being a tiny magnet. Second, the electrons create their own magnetic field, Vecchi bo, right at the location of the nucleus. This field comes from both the electron's orbital motion and its own intrinsic spin.
So nuclear magnet interacts with electrons' magnetic field.
Exactly. And there's a crucial part called the Fermi contact term. This describes the direct magnetic interaction between that nuclear magnetic moment and the spin of an S electron that is literally at the nucleus.
Again, the S electron being right there is key.
Absolutely crucial. That beta-2 factor shows up right in the formula, the result. This interaction splits the electron's energy levels into slightly different hyperfine levels. Measuring that splitting lets us determine the nuclear magnetic dipole moment.
Pi call ma. So it's like the S electron and the nucleus are having a direct, a magnetic handshake because they can literally occupy the same tiny space sometimes.
That's a perfect analogy. A quantum handshake right there at the center.
Incredibly intimate.
Amazing. Is there more?
One more main one. Electric quadrupole hyperfine coupling. This one's generally weaker, but super interesting because it tells us about the nucleus's shape.
Shape? Like if it's not perfectly round?
Precisely. If the nucleus isn't spherical, maybe it's stretched out like a rugby ball prolate or flattened like a discus oblate. And if it has a nuclear spin all 71, it can have an electric quadrupole moment.
Yeah.
This non-spherical charge distribution interacts with the electric field gradient, the EFG, at the nucleus.
Electric field gradient. What's that? Imagine the electric field created by the electron cloud around the nucleus. If that cloud isn't perfectly symmetrical, the strength and direction of the electric field changes rapidly as you move across the tiny volume of the nucleus. That spatial change, that unevenness, is the gradient.
Ah, okay. So a lopsided electron cloud creates an uneven field.
Right, and a non-spherical nucleus feels that unevenness. Now, here's the kicker. Remember how orbitals are perfectly spherical?
Yeah.
Well, a perfectly spherical electron cloud produces 0 electric field gradient at the nucleus.
So S electrons don't cause this interaction.
Correct. This quadrupole interaction is only significant for electrons in p, d, or f orbitals. Their non-spherical directional shapes are exactly what create the necessary EFG to interact with a non-spherical nucleus.
Wow. Okay, so let me see if I've got this. The specific shape of the electron's orbital determines which nuclear property it's most sensitive to.
You've nailed it.
It's like the electron cloud is this incredibly sophisticated, custom scientific probe. You use S electrons to measure nuclear volume or magnetic moment. But you need P, D, or F electrons, the non-spherical ones, to get information about the nucleus's actual physical shape.
That's it, exactly. The orbitals act as active filters, choosing which nuclear whisper gets amplified.
That's incredibly elegant.
Just wow.
So we've learned how the nucleus manages to whisper its properties, size, magnetism, shape, out to the electron cloud. But this really pushes us to ask the deeper "so what" question, doesn't it? Where do these nuclear properties actually come from? What's the ultimate source of these whispers?
Right. That takes us back into that seething sea we talked about, back to quantum chromodynamics, QCD. Let's take nuclear spin, for example. For a long time, people sort of assumed, reasonably maybe, that a proton spin was just the sum of the spins of its 3 valence quarks. Simple addition.
Seems logical.
It does. But then came the experiments in the 1980s, particularly at CERN, led to what's now famously called the proton spin crisis.
Crisis. What happened?
The shocking result was that the quark spins only accounted for maybe 30% of the proton's total spin, just 30%.
Whoa, where's the rest coming from?
Exactly. It was a huge puzzle, a bombshell, really. It forced a complete rethink. We now understand that the total spin of a proton or neutron is much more complex. It's a sum of several things. The intrinsic spin of the quarks, yes, but also the intrinsic spin of the gluons. Delta.
Rest have spin, too.
They do. And crucially also the orbital angular momentum of both the quarks and the gluons as they whirl around inside the nucleon.
So it's spins and movements.
Spins and movements, all contributing. So that nuclear spin that drives the magnetic hyperfine interaction we measure with electrons, it's not simple quark addition at all. It's a truly emergent property of that whole dynamic interacting system of quarks, gluons, and their complex motions. It's a direct reflection of the collective non-perturbative physics of QCD.
Non-perturbative meaning you can't just calculate it easily step by step.
Pretty much. The interactions are too strong, too complex for simple approximation methods. You need powerful theoretical tools and supercomputers. And it's the same story for nuclear shape and size that we measure via the quadruple coupling and isotope shift. These are also collective phenomena. They reflect the average arrangement, the dynamic interplay of all the protons and neutrons packed together, governed by those incredibly complex residual strong forces between them. It's not just about individual quarks in isolation.
So putting it all together, the synthesis here is just it's profound.
Wow.
When we do high-precision atomic spectroscopy using that low-energy electron like a tiny voltmeter, we're not just measuring something simple about the electron or even just the nucleus. We're actually measuring a collective outcome of the super high-energy, incredibly complex physics of QCD that roar from the quark-gluon sea detected through these incredibly faint, delicate whispers felt by the electron.
That's a beautiful way to put it. Physics bridging truly vast scales of energy and distance, all within the tiny atom.
What's really remarkable, then, is that these subtle whispers, these tiny hyperfine effects, aren't just curiosities for physicists. They've actually been harnessed, haven't they, to create some incredibly powerful technologies we use every day.
Oh, absolutely. The applications are widespread and fundamental. Take nuclear magnetic resonance, NMR spectroscopy.
Ah, NMR, yes. Hugely important in chemistry and medicine. MRI is related, right?
MRI builds on the same fundamental principles, yes. Yeah. NMR itself is a cornerstone for figuring out molecular structures. It works by using nuclei that have that non-zero spin we talked about.
The tiny nuclear magnets.
Exactly. You put your sample in a strong external magnetic field, and then you hit it with radio frequency waves. These waves can cause the nuclear spins to flip between their different energy levels.
Okay.
But here's the crucial connection. The electrons surrounding each nucleus subtly shield it from the external magnetic field. They create their own tiny counterfield.
Ah, shielding.
And the amount of shielding depends very precisely on the local electronic environment, what atoms and bonds are nearby. This means nuclei in different chemical groups will experience slightly different local magnetic fields, and so they'll absorb radio waves at slightly different frequencies to flip their spins.
That's a chemical shift.
That's the chemical shift.
Yeah.
Chemists use it constantly. So by precisely measuring these nuclear spin flip frequencies, you're actually mapping out the detailed electronic environment of the molecule, using the nucleus to probe the electron.
Clever. What else?
Then there's Nussbauer spectroscopy. This is an incredibly precise technique using gamma rays. It relies on the recoil-free emission and absorption of gamma rays by nuclei embedded in a solid lattice.
Recoil-free.
Yeah, the crystal lattice absorbs the momentum kick, so the gamma ray energy is extremely well-defined. This allows Nussbauer spectroscopy to directly measure those tiny hyperfine parameters we've been discussing with fantastic precision.
What does it tell you?
It reveals several things, often used for materials containing iron, for instance. It measures the isomer shift, which is directly related to the electron density at the nucleus. Remember the volume effect. This gives clues about the atom's oxidation state, its chemical bonding.
Okay.
It also measures quadrupole splitting. That's the nuclear shape interacting with the electric field gradient from the electrons. It tells you about the local symmetry around the atom, its electronic spin state.
Right, the shape interaction.
And it can measure magnetic hyperfine splitting, which tells you about any internal magnetic field at the nucleus, perhaps from surrounding magnetic atoms, gives an incredibly detailed picture of the local atomic and electronic environment.
All from those tiny energy shifts.
All from those tiny shifts. But maybe the ultimate technological application, the one that affects basically everyone, is atomic clocks.
Ah, the definition of the second.
Exactly. The SI second, our fundamental unit of time, has been defined since 1967 based on an atomic transition. Specifically, it's a transition between the two hyperfine levels of the ground state of the cesium-133 atom.
Hyperfine levels. So this uses the interactions we've been talking about.
It uses the magnetic dipole hyperfine interaction, precisely. It's the interaction between the magnetic moment of the cesium nucleus and the spin of its single outer valence electron.
The handshake.
The quantum handshake. This transition frequency is incredibly stable, oscillating at, get this, 9,192,631,770 times per second. That unwavering stability comes directly from these fundamental quantum interactions.
9 billion times a second.
And that stability is the basis for global timekeeping, for GPS, for so much of our modern infrastructure, all thanks to a subtle whisper between the nucleus and an electron.
So we've really taken quite a journey here, from the fuzzy electron clouds deep into the frantic quark-gluon sea inside the nucleus. We grasped the vast energy gap separating them, and then we marveled at how these tiny, delicate perturbations, the hyperfine interactions, managed to bridge that chasm. And we saw how electron orbitals aren't just passive bystanders. They act as these exquisite, active filters, choosing precisely which nuclear secrets get revealed. It really is an extraordinary dance of scales.
It truly is. And tracing that dance, I think we've seen this profound synthesis emerge. These subtle, almost imperceptible shifts in the electron's energy levels, which we can measure with, frankly, astonishing precision. They do more than just confirm our models of atoms. They carry these faint whispers, these echoes, from the incredibly violent, complex, dynamic dance of quarks and gluons confined deep within the nucleus. And it's that fundamental dance, governed by QCD, that ultimately dictates the properties of the nucleus, which in turn dictates the structure of atoms, molecules, and indeed all the observable matter that makes up our universe, from the small scales to the largest.
It's truly mind-bending when you think about it all connecting like that. Okay, here's something to leave you with, maybe a final thought to mull over. We've talked about the space between the electron cloud and the nucleus, but consider this. Even that empty space isn't truly empty. It's a vibrant quantum vacuum fizzing with virtual particles.
The quantum foam.
Right. And its fluctuations, they cause effects like the Lamb shift, another tiny shift in electron energy levels. It represents yet another layer of subtle, profound interaction constantly happening within the atom, constantly shaping the very energy levels we've just spent this time exploring.
Always more layers to uncover.
Always more layers. Keep that curiosity alive, everyone, and keep diving deep into the hidden realities all around us.